All right, section 11.5, the alternating series test. This section is a relatively short section. There's not much to this. It's a pretty straightforward test that we can use with, well, alternating series. The biggest issue with this one, though, the biggest caution is, and I guess you could say that about any of these tests that we're talking about, making sure that we apply the test correctly. You know, as we always talk about, like with theorems, don't read more into what the test says. Don't make improper conclusions based upon the information that you gather. Right. So be clear on what the test says. Don't make any presumptions beyond what is stated. So the alternating series test, obviously, like we said, deals with series that are alternating. How do I recognize an alternating series? Primarily, it's going to be these types of series, right, where we see this -1 to the n, or -1 to the n minus 1, or -1 to the n plus 1. So we talked about taking -1, raising it to successive powers, right, for n equals 1, 2, 3, 4, etc. And you're going to get an alternating negative, positive, negative, positive. Now, depending upon, and this kind of dictates what that exponent is going to be, whether it's n minus 1, n plus 1. A lot of it has to do with your subscript, with your index on the series. And if you want that first term in the series to be positive, or you want the first term to be negative, you can adjust either the counter for n, start at 1 or 2, or you even see some with 0. We haven't seen one of those yet, but we saw one where n equals 2 was our starting point. Or you can adjust the -1. Right? So if I start, say, for example, with n equals 1, -1 to the n, with the first term there would be negative, right? -1 to the first. If instead of -1 to the n, say I put -1 to the n plus 1, then my first term would be -1 squared, right, which would give us a positive value, right? So you can adjust positive versus negative based upon either where you start your counter or the exponent on the -1, right? So for this one, we're looking at -1 to the n times square root of n over 1 plus 2 square roots of n. Right? So I've written out the first few terms of that, -1/3 plus square root of 2 over 1 plus 2 roots of 2, etc., etc. And again, all those are just the terms that are formed by plugging in values for n. Generically, we're looking at a series that can be written in the form of, like we said, -1 to a power times what we're calling this b sub n, where b sub n is the positive part of that term. Right? So when we look at this series up top, square root of n over 1 plus 2 square roots of n, that's what we're calling the b sub n. It's the absolute value of the terms of the series. Right? And if you apply that absolute value to a sub n, then you simply you're ignoring the -1 part. Right? So the generic notation, an alternating series is a series of the form -1 to a power times some positive expression, right? Which, again, that's just the absolute value of a sub n. Then the alternating series test says that if we have an alternating series that fits that format, and the series satisfies those two requirements, in that b sub n plus 1 is less than or equal to b sub n for all n. In other words, the absolute values are decreasing, because, again, remember, that's what b sub n is. It's the absolute value of the terms of your series. And if the limit as n approaches infinity of b sub n is 0, then we have a convergent series. Right? Now, that second requirement, this, is actually with reference to, remember that test for divergence that we start out with? We said the limit as n approaches infinity of a sub n has to equal 0 in order for the series to be convergent. Well, this is telling us that the same thing has to be true for the absolute values of the terms of our series if we have an alternating series. Okay? So that makes sense that that would have to be true. Now, again, if that's not true, then you have a divergent series. right? And that's test. That's still basic test for divergence. So I always recommend that you check that first. Look at your limit as n approaches infinity of the absolute values of the terms, because if that's not equal to 0, then you have a divergent series by the test for divergence, right? Now, the other requirement, that b sub n plus 1 less than or equal to b sub n, says that the absolute values of the terms of our series have to be decreasing, right, for all values of n. So you have to have a decreasing absolute value, and you have to have that limit equal to 0. Now, the checking for this decreasing terms, that's not something that I require a lot of formal work for. I mean, you can make some observations about that, or just I'll allow you to write out the first few terms, because otherwise, I mean, you can get into a whole discussion about, well, how do I determine if the terms of the series are actually decreasing? Well, I mean, we've made some observations about, increasing denominators means the term would be decreasing, right? But in some cases, it's not that obvious. You may have to list out a few terms to see if they are actually decreasing, but like we always say with that, the first few terms doesn't tell me what's happening as we approach infinity necessarily. It just gives me an idea of what may be happening. But we'll take that to be sufficient. Otherwise, you have to start looking at derivatives. You can say, look at the derivative of a sub n. Because remember, what does the derivative tell us? The derivative tells us if it's an increasing or decreasing function. If we put it in that context, replace n with x and talk about it in terms of the function of x instead of the function of n, right? And if our derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing, right? So you can look at the derivative and see if the derivative is negative for all values of n or all values of x, right? And then by that observation, you could say that the series would be decreasing. And you'll see them do that when you're looking at the solutions manual and determining this part of this requirement, if it's a decreasing absolute value. You'll see them do that. So that's what's going on there. They're using the derivative and say, okay, look, hey, the derivative here is negative for all values of n, so therefore the series has to be decreasing. Okay, but check number 2 first. That's always your first best option, because we know that has to be true regardless. But now again, that is test for divergence. So if number 2, the limit is n approaching infinity of the absolute values of your terms, is not equal to 0, then I could say the series is divergent, but it's by the test for divergence, not by the alternating series test. And that's what I was talking about earlier. Don't misinterpret what the test says. So in order for what does alternating series test tell me? If those 2 requirements are met, I have a convergent series. Otherwise, what does it tell me? It tells me nothing. Okay? So if I don't match or meet one or both of those requirements, okay, that tells me nothing in terms of alternating series test. All right, so for example, so looking at the one that we started with, so at -1 to the n, square root of n over 1 plus 2 square roots of n. And again, I've done some approximations there to show us, first of all, that look, the values of the terms are not even decreasing. The absolute values of the terms of that series. So again, just that observation right there tells me that it's I can't use alternating series test necessarily, right? Because the absolute values are not decreasing, and that's one of our requirements. Also, though, if you look at that test for divergence, if I look at the limit as n approaches infinity of the absolute value, right, of the terms of our series, that gives me 1/2. Right, now again, how do I get that? Divide everything by square root of n, and that would give you 1 over the square root of n plus 2, which equals 1/2. I guess I'll write that out. So just to remind us, so if I'm looking at the limit as n approaches infinity, of square root of n over 1 plus 2 square roots of n, right? I mean, and again, I mean, you could go through the whole L'Hopital's rule thing, but dividing everything by square root of n is where we're getting this limit as n approaches infinity. Divide by square root of n up here, and I've got 1. Divide by square root of n in the denominator, you've got 1 over the square root of n plus 2, right? And as n approaches infinity, that's going to 0. giving us a value of the limit at 1/2. All right. So just to be clear, I don't want any misunderstandings there. But yeah, so we're testing that the limit of the b sub n, right, the absolute values of our terms, and that's equal to 1/2, which is not 0. Right? So I can tell you that that series diverges, but it's by the test for divergence. In other words, you never say that a series diverges because of alternating series test. Alternating series test can be used to show that a series is convergent. Okay. And then this fact that the terms are not equal to 0, the limit as n approaches infinity, that's test for divergence. Right? So you want to be clear there, because I said one of your requirements is once you make the determination about convergence or divergence, you have to be able to state or give the reasoning for it, right? Which test did you use, or according to what test? So be careful there. The second example, from 2 to infinity, of -1 to the n minus 1 times 1 over square root of n. And again, the terms just written out, but that's a pretty straightforward series. I think if we look at the absolute values, right, the b sub n is 1 over the square root of n. As you increase the values of n, right, we increase the denominator, we know the fraction is decreasing. Right? That's one of our pretty standard observations. So I can tell you that b sub n plus 1 is less than or equal to b sub n. The absolute values are decreasing. And then if we look at the limit as n approaches infinity of 1 over the square root of n, again, a pretty standard observation. As n increases, square root of n increases, 1 over the square root of n approaches 0. Right? So we do have the two requirements. We have that the series is decreasing, the absolute values, and we have that the limit of the terms, the absolute values, is 0. And so then I could say that this series is convergent by the alternating series test. Right? And that's pretty much it. I mean, that's what alternating series test is. Like I said, the biggest concern with this one is just not misinterpreting what it tells you. Right? And then also, again, like I said, always check that second requirement first. Make sure the limit as n approaches infinity, the absolute values is 0, because if that's not true, then the series diverges by the test for divergence. Okay. All right, that's it for that section. See you in section 6.